Hi everyone, welcome to another linear algebra tutorial. In this tutorial, we will be identifying which square matrices are singular and which matrices are non-singular. So hence, we will be doing a singular versus non-singular square matrices. We'll be taking a look at some examples to see which square matrices are singular and which are not. So now we are given two matrices. We are supposed to determine which is non-singular and which one is singular. So let's start off with the first one, which is this. So what's our first step again? We associate it with a homogeneous system, as you can see over here. After this, we abbreviate this homogeneous system with this matrix. This is the augmented matrix. So as you can see, just like what we always do, we will want to eliminate the x variable on the second row. Hence, we add minus 4 times our row 1 to row 2. And the working is over here, as you can see. So the left hand side will go as minus 4, x plus 3y plus 4x minus 12y will give me minus 24y. And on the right hand side, it will give me a constant of 0. Hence, this will be our new working, as you can see over here. So now, since this matrix of coefficients of the homogeneous solution have a x and y as leading variables, and every row has a leading variable, therefore, this matrix of coefficients has a unique solution, and this makes this matrix of coefficient non-singular. Let's go through the second example. Now we are given this. So first step again, we associate it with a homogeneous system, as you can see over here. And after this, same thing, you want to eliminate the x variable on the second row. Hence, we add, but before this, we abbreviate this homogeneous system with this matrix. And after this, we add minus 4 times our row 1 to row 2. So the working is over here, so left hand side will go to 0 and the right hand side will go to 0. So there's no variables on the second row and there will be a 0 constant. And now, as you can see, this second row has no leading variable, and hence y is not a leading variable. So hence, since the matrix of coefficients has a non-leading variable, therefore it has infinitely many solutions, and this makes it singular. We can only apply this kind of thing. We can apply whether the system is singular or non-singular, depending on whether it has a unique solution or many solutions, only when the matrix is a square matrix. So let's take a look at another example. So which of these are singular or non-singular? We have two examples here. But if you were to notice for the first example, it is not a square matrix. So let's go into detail the first example, which is this. So how do we solve this? First, we find its transpose. In the earlier lesson, we have already learned how to calculate the transpose of a matrix. Hence, the transpose of the matrix is written as this. So, with this transpose of the matrix, we can multiply A by its transpose, which goes as this. So this times this, a scalar multiplication will give me this, and this will be our matrix, which is multiplied by its transpose. And after this, we associate it with a homogeneous system since it's already a square matrix. Hence, this is ours. And after this, we abbreviate this homogeneous system with this matrix. So now you notice that the second and third row, for the second and third row, the second row has a higher coefficient of x than the third row. Hence, we swap row 2 with row 3. And this will be our transform row. And after this, we can add minus 1 times of row 1 to row 2 and minus 5 over 2 times of row 1 to row 3. And the working is all shown over here. For the left hand side, we get 0 and the right hand side will go to 0. And the same goes for this. So left hand side will go to half y and the right hand side will go to 0. And after this, we can swap row 2 with row 3 and we can get our system in echelon form. Hence, we can solve the system. So now we can see that the third row has no leading variable. And since the system has at least a non-leading variable, therefore the system has infinitely many solutions, and this makes the matrix of coefficient singular. Now let's go through the last example, which is this. So now we associate it with a homogeneous system, this, and the next step, we abbreviate this homogeneous system with a matrix, as you can see over here. And after this, you want to eliminate the x variables on the second and third row. We add minus 1 times of row 1 to row 2 and minus 3 times of row 2 to row 3 to obtain this matrix. So the final step, you want to eliminate the y variable on the third row. Hence, we add minus 2 times, we add 2 times of row 2 to row 3, minus 2 times of row 2 to row 3. Hence, we get it in this form. And the workings are all here again shown. You can take a look later when you replay the video. And now, since we got our system in echelon form, we can already see that the last row has no leading variable. And since the matrix of coefficient has at least a non-leading variable, it has infinitely many solutions. Hence, it is singular. So we have already come to the end of this tutorial. Let's do a quick recap. What makes a coefficient, what makes a matrix, a square matrix singular, is that when we make it to an echelon form and we found that it has infinitely many solutions, and non-singular is that when it has a unique solution. After converting to echelon form,